Alright, so in terms of computing things like the derivative and limits in general, we want to make life easier for ourselves, and so here is a video which describes ways to make life easy. And what we need to talk about are limits and a concept called continuity. And so the first real thing that we've seen as we've been computing some of our limits is that sometimes the limit that you get, you could have just plugged in your value for the variable for f of x. And so the question is, when can we use that technique and when can't we? And if we had a list of functions that we could just always use this technique for, then when we go about computing limits, especially for computing the derivative, it would save us a whole lot of time. We wouldn't have to use the limit laws, we wouldn't have to try to plug in values, everything would be much happier. And so what we're kind of asking is, when is the limit as x approaches a of f of x equivalent to f of a? And it turns out that the right answer for this is when f of x is continuous at x equals a. And if you go back and we look at that definition, the definition of continuity really is when the limit equals the value of the function. And since we're not going to be doing rigorous delta epsilon limits, we're really not going to be able to view it from that angle, so instead I'm going to give you a list of continuous functions, and you'll be able to use that list to just plug it in instead. And so if you look over on the graph on the right, and you imagine walking along the green line to that point, you can remember that the sort of feel-good first definition you get for continuous is that a function is continuous if you can draw it without picking up your pencil. And so over there on the right, what you want to imagine is, well, what does it mean to be continuous going closer and closer to that point for f of a? And if we can't pick up our pencil, then f of a must be defined, otherwise you'd pick up your pencil, and the line must go into f of a and leave f of a, otherwise if it didn't, you'd have to pick up your pencil again. And so continuous means that f of a exists, that the limit as x approaches a of f of a exists, and that they're the same thing. And so there's a good feeling for what the definition of continuous means and why we define it that way. And if you had a list of these continuous functions, then you could just take limits real easy. You would just have to plug in a to f of x. And so here's a list of functions. We're going to start with polynomials. Polynomials are the nicest functions we have. Polynomials are smooth, continuous, they have nice turning points, things like that, everywhere. And since they're continuous for all values of x, you can always just plug in the value you're heading towards. And so each of these comes with an example. Go ahead and look at the example and convince yourself that it makes sense. Rational functions. Now, rational functions are a fraction that has a polynomial up top and a polynomial down below. And so rational functions are continuous everywhere they're defined. And so an example of a rational function, which is defined at our point, is this 3x minus 1 over x plus 2. Since we're going to 1, we're not hitting a 0 in the denominator, right? This function only has a problem back at negative 2. And so the limit of 3x minus 1 over x plus 2 as x goes to 1 is just 3 times 1 minus 1 over 1 plus 2. Now, here's a trick, and we'll talk about this later in the video too, and we've talked about this before, but this limit is not defined as we go to 2 because, at least as we've written it, it's not going to work because the limit of the top and the limit of the bottom are both 0, right? And so that's bad. We have something with 0 on top and 0 down below. However, this function, the limit as x goes to 2 of x plus 2, that's defined when x equals 2. And so over here on the right, we can see that if we factor the top of x squared minus 4 over x minus 2, we get x minus 2 times x plus 2. And so we have this x minus 2 on top and bottom that could cancel. And in fact, they do cancel whenever x is not equal to 2. And if you look back over at the original limit, even though that function's not defined at 2, that doesn't matter because the limit never cares what happens at 2. It only cares what happens nearby. And since it only cares what happens nearby, we can actually say those two limits are equal. And so the limit of x squared minus 4 over x minus 2 is just the limit as x approaches 2 of x plus 2, which is 4. Now, the exponential functions are continuous absolutely everywhere. So you can plug in the value you're looking for if it's just a plain exponential function like 2 to the x or e to the x or whatever. Logarithmic functions are continuous everywhere that they exist. And so the limit as x approaches 1 of log 2 of x is just log 2 of 1. And 2 to the 0 is 1, so log 2 of 1 is 0. Trig functions are continuous everywhere they exist. And so you can take the limit of tangent as long as you're not trying to take it at pi over 2. For that you have to do something else. And you could take the limit of cosine everywhere because cosine's defined everywhere. Now roots. We have different types of roots. We have square roots and cube roots and fourth roots and so on. We split roots into two types, the evens and the odds. The odds are actually easier, so we talk about them first. Odd roots are continuous everywhere. So if you're trying to take a limit of a cube root, then you can just go ahead and take the cube root of the value. But if you have even roots, they're going to be continuous when the thing underneath the root, which is called the radicand, they're continuous when the radicand is greater than 0, and they generally have one-sided roots when the radicand equals 0. So for example, the limit of the fourth root of x, as x approaches 1, since 1 is bigger than 0, the limit's just going to be the fourth root of 1. However, here we have an example of the limit as x approaches 0 of the square root of x. If we let x go to 0 from the right, well then those values are all bigger than 0, and so we can just take the limit by plugging in 0. But if we go on the left, since all those numbers are negative, all the numbers to the left of 0 are negative, the square root of x doesn't exist over there. And what you want to think about is the graph of the square root of x looks like this. And so over here, there's just nothing. And the limit looks at a bunch of nothing and says the limit must also be nothing. And so the limit on the left doesn't exist. And since the limit on the left doesn't exist and the limit on the right does, and those two concepts don't agree, the limit in general does not exist. Now, the last thing I want to say is if you have a fraction in your limit and it looks a lot like 0 over 0, what you want to try to do is do some sort of factoring or something like that in order to get an equivalent function, something that's the same except for at that point, and then you'll be able to take the limit. And so I have two examples for you. The example 1 is that x cubed minus 8 over x minus 2 looks like x squared plus 2x plus 4, except at x equals 2. The polynomial is defined, the rational function isn't, but since they're the same function everywhere else, the limit of the one is the limit of the other. And since the limits are the same, and we can easily take the limit of the polynomial, we see the limit of x cubed minus 8 over x minus 2 is just 12. Also, we have rad x minus 2 over x minus 4. If we try to plug in 4, we get 0 over 0. But if we multiply top and bottom by the square root of x plus 2, the x minus 4 will cancel with the x minus 4 we get up top, and we'll be left with 1 over radical x plus 2. And so since they're the same, everywhere except at 4, we can take the limit as x goes to 4 of the function on the left by taking the limit as x goes to 4 of the function on the right. And we wind up getting a quarter. And so we see the limit as x goes to 4 of radical x minus 2 over x minus 4 is just 1/4, even though that function is not defined at 4. And so that's it. I want you to go ahead and think about how you would use the new information about continuous functions to take limits easier. Go ahead and do the little homework associated with this, and then I'll talk to you later.